Our planet is a world of constant change. From a distance it appears serene and stable, a blue marble in space. The thin atmosphere glows at the edge, yet this placid image conceals a dynamic, evolving story. Earth is not a static rock. It is a living, breathing system. Its surface has been sculpted and resculpted over immense timescales. Mountains rise and fall, oceans open and close. Continents drift across the face like colossal rafts on a slow, molten sea. This story is written in the very ground beneath our feet. Our story does not begin on Earth. It begins in the vast, cold emptiness of space. Some 13.8 billion years ago, the Big Bang. In the first moments, only the simplest elements were formed: hydrogen, helium. For millions of years they drifted, but gravity, the silent architect of the universe, slowly began to pull them together. Great clouds of gas coalesced, collapsed, ignited into the first stars. Inside stellar furnaces, heavier elements forged: carbon, oxygen, iron, forged in the hearts of dying stars. Those stars exploded, supernovae scattering elements. Enriched stardust mingled with primordial gases, forming molecular clouds. One cloud, a swirling nebula, destined to become our home. About 4.6 billion years ago, a nearby shockwave disturbed it. That disturbance triggered gravitational collapse. The cloud shrank, spun faster, flattened into a rotating disk. The protoplanetary disk, the birthplace of our solar system. Over 99% of the mass was drawn inward. That concentration ignited to form our sun. The outer disk remained a thin cosmic nursery. Early Earth was a molten ball of magma. That intense heat enabled the next stage of evolution. Materials moved and separated internally. This set the stage for Earth's layered internal structure and eventual crust. The heaviest materials were pulled by gravity towards the center: iron, nickel. This great migration of dense metals marked the birth of Earth's core. As the iron descended, as the nickel descended, they displaced the lighter materials, forcing them upwards. This vast, thick layer of silicate rock became the Earth's mantle. The motion of liquid iron in the outer core established Earth's magnetic field. This magnetic field extended far out into space, creating the magnetosphere. This shield was crucial for life on Earth. As the surface of the magma ocean was exposed to the cold of space, it began to cool and radiate its heat away. Temperature dropped enough for the first solid minerals to crystallize from the molten rock. The very first minerals were dense, magnesium-rich silicates like olivine. These early crystals sank back into the mantle. Eventually, lower-density minerals such as feldspars began to crystallize. Feldspar crystals floated to the top like slag in a smelter. This was the birth of Earth's very first crust. The first crust to form on Earth was anything but stable. The underlying mantle was much hotter and convecting far more vigorously than today. This intense churning pulled the thin crustal plates apart. In other places, sections of the cold, dense crust would founder and sink back into the hot mantle. Any given piece of the primordial crust likely had a very short lifespan. As the Hadean Eon gave way to the Archean, the relentless bombardment from space began to subside. With fewer giant impacts, the planet could cool more steadily. That cooling changed the atmosphere dramatically. The thick, steamy blanket of water vapor could now begin to condense. The skies opened in a rainfall event that lasted millennia. The Great Deluge began to fill the low-lying basins of the young Earth. These early oceans were not blue. They were likely acidic and rich in dissolved iron, murky and greenish. Over millions of years, shallow seas coalesced into global oceans. Their presence changed Earth's path geologically. Liquid water transformed crust formation. Water acts as a flux, lowering mantle rock melting points. Oceans enabled erosion and sedimentation. Primitive land masses were weathered and worn down. Sediments were carried by water and deposited in ocean basins. As Earth's surface processes matured, a fundamental dichotomy emerged. The crust was not a single uniform layer. It began to split into two distinct and enduring types: oceanic crust and continental crust. Oceanic crust is what lies beneath all of our planet's major ocean basins. It is relatively thin, typically only about 7 kilometers thick. It is also quite dense. It is composed primarily of mafic rocks. Continental crust, by contrast, is the foundation of the land masses we live on. It is much thicker than oceanic crust, averaging about 35 to 40 kilometers. Crucially, it is less dense. This lower density gives continental crust its characteristic buoyancy. It floats higher on the underlying mantle. This is why continents rise above sea level. A key characteristic of oceanic crust is its youth. It is constantly being created at volcanic ridges on the seafloor and destroyed in other areas. As a result, continental crust is, on average, much older than oceanic crust. They are the great, ancient archives of Earth's history. The formation of oceanic crust is continuous and beautifully simple. It happens at mid-ocean ridges, a vast underwater mountain chain, a boundary where tectonic plates pull apart. As the plates separate, pressure on the hot mantle drops. Decompression causes mantle rock to partially melt. That partial melting generates basaltic magma. When the magma reaches the seafloor, it erupts. Contact with cold ocean water cools it rapidly. Bulbous pillow lavas form. New crust is then pushed away from the ridge on both sides, like two immense conveyor belts. As crust moves away, it cools and contracts. The story of continental crust is far more complex. The primary locations for making new continental crust are subduction zones. As the subducting plate descends, heat and pressure release water from its minerals. This water rises into the overlying mantle wedge. The addition of water dramatically lowers the melting point of the mantle rock. Some of the magma erupts on the surface, forming chains of volcanoes. The surface of our planet is a mosaic of massive, rigid slabs of rock that are in constant, slow motion. This is the theory of plate tectonics. These slabs are called lithospheric plates. They're made of the crust and the rigid upper mantle. These plates float upon a hotter, weaker, more fluid layer of the mantle known as the asthenosphere. One key mechanism: ridge push. At mid-ocean ridges, the ridge sits higher, creating a gentle slope. Gravity pulls the new, hot, buoyant crust down that slope, pushing the plate away. A stronger force: slab pull. When an old, cold, dense oceanic plate reaches a subduction zone, it sinks back into the mantle. Its weight pulls the rest of the plate. Together, these forces keep plates moving. Plates slide past one another. They collide with immense force. They pull apart to make new crust. These boundary interactions are where Earth's geological drama unfolds. It explains why volcanoes and earthquakes cluster in zones like the Ring of Fire around the Pacific. The slow dance of tectonic plates over vast stretches of geological time has led to a recurring pattern of continental assembly and dispersal. This is known as the supercontinent cycle. At certain times, most or all of the continental crust has gathered to form a single, immense landmass, a supercontinent. The most famous was Pangaea. The evidence is written in the rocks, fossils of the same land-dwelling plants. Geological structures and rock types of eastern South America match those of western Africa. These colossal continents are not permanent. After hundreds of millions of years, they are torn apart by mantle forces, breaking into smaller drifting continents. Earlier supercontinents, Orogenic. Earlier still, Columbia. The cycle timescale, roughly 300–500 million years. Right now, a dispersal phase after Pangaea's breakup. The Atlantic Ocean is widening. The Pacific Ocean is shrinking. Far in the future, the continents will converge again. While plate tectonics constantly reshapes the edges of continents, their deep interiors often remain remarkably stable for billions of years. These ancient and stable blocks of continental lithosphere are known as cratons. Cratons are characterized by thick, cold, buoyant lithospheric roots that extend deep into the mantle. These deep roots act like the keel of a ship, stabilizing the overlying crust. Cratons are composed of the oldest rocks on Earth. The surface exposures of these ancient rocks, where they are not covered by younger sediments, are called shields: the Canadian Shield, the Brazilian Shield, the Western Australian Shield. They are also tectonically quiet, with very few earthquakes or volcanic activity. The formation of cratons marks a critical step in crustal evolution. They represent the point when portions of the continental crust became thick and buoyant enough to resist being recycled back into the mantle. These ancient cratons are not just geologically stable, they are also the storehouses of many of the world's most valuable mineral resources, like diamonds, gold, and iron. We will then look at orogeny, the process of mountain building. This happens when tectonic plates collide, crumpling and uplifting the crust to create ranges like the Himalayas. We will also see how the crust is shaped not just from within by endogenetic forces, but also from without. Exogenetic forces like wind, water, ice relentlessly weather and erode the surface, carving landscapes and transporting sediment across the globe. This story is also one of human curiosity and discovery. Geological science is our tool for answering that question. Through careful observation, analysis of rocks, and sophisticated technology, we have pieced together the incredible history of Earth's crust. The ground we stand on is a product of cosmic origins and ceaseless geological forces, a heritage of deep time that connects us to the very beginning of our solar system. To understand the crust is to appreciate the immense, powerful, and delicate systems that make Earth a living planet, a unique and precious home in the vastness of the cosmos.